Okay, let's go ahead and start looking at some trig functions with right angles. So this is normally the way we first try and define trig functions. Actually not, let me change that, right triangle. Not just right angle, right triangle. Right triangle is normally drawn this way. The little square indicates that that angle is a 90-degree angle. And normally, we go over here and we define one of the other angles. Our triangle is theta. So here's a right triangle. Now there are two key points about right triangles that we're going to need to use all the time. Let me even write them down. Key points. The first is, anytime you have a triangle, which includes a right triangle, if you add up all three angles of the triangle, so the sum of the three angles of the triangle has to equal 180 degrees. As a matter of fact, in this whole talk, we're going to be working with angles in degrees for right now. But anyways, the three angles of any triangle have to equal 180 degrees. Now for a right triangle, we have something a little special going on because we know one of our angles is always 90 degrees. So basically we know that the other two angles have to equal also 90 degrees. But I think that's pretty obvious. Now a second key point concerning a right triangle is that we can apply I hope I spell it correctly, Pythagorean formula, which is a formula that only applies to right triangles. Now, if you recall from geometry, when we define the Pythagorean formula, we draw a right triangle. The longest side, the side opposite the right angle is called the hypotenuse. And then these two sides are called the legs. Matter of fact, normally the length of the leg, this first leg is called A, the second leg is called B. And actually, normally the hypotenuse, we just call the length of the hypotenuse C. And what Pythagorean came up with was this very famous and helpful equation that says for a right triangle, you can take the hypotenuse and you square it, and that equals, you take your first leg and you square it, and you add it to the square of the second leg. All right, so that's the very famous and very useful formula called the Pythagorean formula. Basically, what the Pythagorean formula says is, if I know two sides of a right triangle, I can use the Pythagorean formula and figure out the third side. So really, these 2 points, one deals with angles and one deals with the sides of the triangle. The first one says, you know what? If all three angles equal 180, if I know two of my angles of a triangle, then I know the third angle. Pythagorean formula says, you know what? If I know two sides of a right triangle, then I know the third side. And actually, if we're talking about a right triangle and the three angles, we even know more. Because you know one angle's 90, so really, if we know for a right triangle, if we know one of the angles, then we automatically know the other angle. Just for example, to make that clear, if I have a right triangle and I say this angle is 50 degrees, I know right away that that angle must be 40 degrees because these three angles have to equal 180. And for the Pythagorean formula, a quick example. Say, for instance, we know the length of this leg is 4, and just say the hypotenuse is 5. We don't know the length of the side A, but since this is a right triangle, the Pythagorean formula says hypotenuse squared equals one of the legs squared plus the other leg squared. So if I go and try and solve this, 25 equals a squared plus 16. If I subtract 16 from both sides, I get 9 equals a squared. So what would a be? What do you have to square to get 9? A would be 3. So those are two facts about right triangles that we're going to use a lot as we begin to define and look at trig functions. So let's actually start thinking about these trig functions. There are actually 6 trig functions. And in my mind, when I think about these trig functions, I think there are two really important, the two most important trig functions. Then there is the third one that's pretty important. And then the last 3, at least in my mind, are not so important. The first 2 I use all the time for problems. The third one gets used some. The last 3 I rarely use. Even if I have problems with the last 3, you'll see that I quickly convert them and make them look like the important ones. All right, that may not be totally clear, but let me go ahead. Let's just do some quick definitions. Let's assume that we're working with an angle theta. The two important trig functions. First, it's written sin, but it's pronounced sine. We would say sine of theta. When we take a trig function, the trig function relates to an angle. So I've got the angle theta, sine of theta. The second really important trig function, it's written cos, but it's pronounced cosine of theta. Maybe here all right. It's actually sort of as a word, as a word, it's written as sine. And this one we write as cosine. So sine of theta, cosine of theta. Those are the very most important trig functions that we're going to use all the time. Let me label this next one sort of important. And it's one that is tan. It's pronounced tangent of theta. So as a word, it's written this way. Tangent of theta. So the sine and the cosine are definitely the most important. The tangent is sort of important. And then there's three more that, at least in my opinion, are not that important. I don't use them that much. If I have to use them, I quickly change them. And you'll see what I mean by that in a little bit. So the not so important functions, there are three of them. This first one, it's CSC, and we say that's the cosecant. The cosecant of theta. The next one is SEC, which is pronounced the secant of theta. And the last one is spelled COT, and it's pronounced the cotangent of theta. So there they are, the 6 trig functions. We've got the two important ones, sine, cosine. The next one that's pretty important is tangent, and the last three are not that important. Cosecant, secant, and cotangent. So let me go ahead and take a minute now, and let's go look at a right triangle. And I'm going to, with this right triangle, go ahead and define what the sine and the cosine and the tangent means in terms of a right triangle. So let me draw a right triangle again, just like I've drawn before, except now I'm going to put some special labels on this triangle. Once again, right triangle. I'll go ahead. You know, I could make theta this angle up here, but I don't know. It's just a habit. I seem to always make this angle my theta. And now I'm going to label the three sides of my triangle with a special label. And that special label, the special labels are these. The first one we've used before. The side opposite the right triangle, we're still going to call the hypotenuse. That comes from same thing as the Pythagorean formula. So the longest side of the triangle, the side opposite the right triangle, is called the hypotenuse. Now these other two sides, I'm going to name them in relationship to my angle. And you'll see what I mean in a minute. If my angle's here, we like to think of this side as this side is sort of opposite of the angle. And this side, we say it's adjacent to the angle. Since this side sort of touches the angle and helps form the angle, and this side is way on the opposite side of the angle. So we like to call this side the opposite, OPP, and this side we like to label as adjacent. So when you have right triangles, whenever you make your theta, the theta helps define which side is the adjacent and which side is the opposite. Just for fun, I'm going to go over here, and if I had chosen to make this my theta, of course this side is still the hypotenuse, but for this triangle, since this side is now opposite the angle, this would be the opposite, and this one would be the adjacent. So the opposite and adjacent are defined by which angle you call theta. Now, so we don't get confused, I'm going to sort of mark this out. I just wanted to show you that I could have had a separate angle. So now, based upon this right triangle with these definitions, I can now define my three main trig functions. And what happens is the sine of theta it's going to be a fraction, and on the top, let me say real quick, these trig functions all end up being fractions or ratios of two sides of the triangle. All three trig functions. They're all going to be fractions, and the fractions are going to be made up of two sides of the triangle. For the sine of theta, it's always the opposite side over hypotenuse. That's just how sine is defined. The sine of the angle theta is always the opposite side over the hypotenuse. The cosine of theta turns out it's also a fraction, and now it compares the sides of the triangle. We first look at the adjacent side over the hypotenuse. And the third one we'll go ahead and look at is the tangent of theta. It's also a fraction, except tangent says it's the opposite side over the adjacent side. So these are the three key, very important definitions of trig functions. Now, one way to remember these, instead of writing out opposite hypotenuse, a lot of times what we do is we use the little phrase so. So stands for the sine equals opposite over hypotenuse. And in the same way, the cosine, which is adjacent over hypotenuse, we like to just remember the little phrase ka. Cosine equals adjacent over hypotenuse. And then for the tangent, since it's opposite over adjacent, most of us just pronounce it toa. Tangent equals opposite over adjacent. So most trig students, one of the first things they do is they memorize this little three-word phrase called so ka toa. So ka toa. If you memorize that, whenever you need to remember what the sine is, or what the cosine is, or what the tangent is for a right triangle, you know right away. So just to make sure we understand this, let's go ahead. I'm going to draw a right triangle, and we're going to go ahead and give the lengths of the three sides of the triangle. So here's my right triangle. Once again, we'll call this theta. We're going to make the hypotenuse a length of 5. We'll make this bottom leg a length of 4. And the other leg, the other side, a length of 3. And now the question is, please write I'll say give all 6 trig functions. All right, so I go back. I'm going to start out with sine, cosine, and tangent. We've already talked about those. Then after we do those, I'll tell you how to get the other 3. So what I do is I say, well, the sine of theta, I say to myself, so katoa, so, sine, S-O-H. The sine of theta equals the opposite over the hypotenuse. If this is my angle theta, the opposite is this side over here. So it's 3. The hypotenuse is 5. So we can say the sine of theta is 3/5. Cosine, so ka toa. So ka means adjacent over hypotenuse. So if I go back to my triangle, here's my angle theta. Adjacent is the side that actually touches or helps to make up the angle theta. So adjacent's 4, and the hypotenuse, once again, is 5. Oh, I'm sorry. The screensaver times out. I hope this is still recording. I think it is still recording. I don't know what point it blanked out, but I'll do a quick review. So I created this right triangle, and I know the lengths of the 3 sides. It's a pretty famous 3, 4, 5 right triangle. And this is my angle theta, and I've decided to try and find all 6 trig functions. So the sine of theta is opposite over hypotenuse, so 3 over 5. The cosine of theta is adjacent over hypotenuse, which is 4 over 5. And then the tangent of theta is opposite over adjacent, so ka toa, the toa. Well, the opposite side of my angle is 3, and the adjacent side in relationship to this angle theta is 4, so the tangent is 3/4. All right, so based upon the definitions of sine, cosine, and tangent, if we know the 3 sides of a triangle, we can write out the trig functions. But now, I've only written 3 trig functions here. How about the other 3? All right, let's talk about the other 3. And here's some important facts about them. Let's first look at the cosecant. So what if I said I want to find the cosecant of theta for that right triangle? Here's how I always do it. Other people might do it differently, but this, to me, I found is just the easiest way to go about it. As it turns out, the cosecant of theta is really just the inverse, or maybe we can think of it as the opposite of the sine of theta. The way we write that mathematically is we say the cosecant of theta equals 1 over the sine of theta. Now, in a very practical way, this becomes very simple, because here's what happens. If I know the sine of theta and I want to get the cosine of theta, I simply have to flip the sine of theta. Let me write that down. Flip the sine of theta to get the cosecant of theta. That's what it means when you have an inverse. If one of these is a fraction, the way you get the other one is just to flip the fraction. So I go back up here for this triangle. I found the sine of theta to be 3 over 5. That means it's very simple. The cosecant of theta is just 5 over 3. And to be honest, if I'm ever given a problem that involves the cosecant of theta, I very rarely ever work with the cosecant of theta. I would just go into that equation or that expression, and right away I will replace every cosecant of theta with 1 over sine of theta. I just do it right away. I don't deal with cosecants. I just work with sines. Now, in the same way, let's look at the secant of theta. Turns out the secant of theta is the inverse of the cosine of theta. So now the same principle, the same relationship applies between the secant and the cosine. Up here, it's like the cosecant and sine are inverses of each other. Well, in the same way, the secant and the cosine are inverses of each other. So if I'm trying to figure out the secant, all I have to do is see what I got for the cosine and then flip it. The cosine was 4/5. If I flip it, it's 5/4. Now the key thing you have to do here is you have to somehow in your mind remember which goes with which. It's almost like the cosecant and the sine are sort of linked together, and the secant and the cosine are linked together. You have to remember which is which. Please don't start thinking that the sine and the secant are somehow related. They're not. It's cosecant and sine and secant and cosine. All right, so now we have 5 trig functions. There's actually one more, right? And that's the cotangent. The cotangent's the easy one because it's actually the inverse of the tangent. Cotangent, tangent, very easy to remember that those are related. So if I want to find the cotangent of this angle theta for this triangle, I simply go and take my tangent and I flip it. If the tangent of theta is 3/4, the cotangent must be 4/3. Now before I close out this little lecture, let me give you one more very, very important relationship that's used all the time. And that's a relationship that actually shows how the 3 important trig functions are also related in a special way. So I'm talking about sine, cosine, and tangent. How are they related? Well, as it turns out, the tangent of theta is always going to be a ratio or a fraction of sine over cosine. That is a very, very useful fact that gets used all the time. The tangent equals the sine over the cosine. As a matter of fact, sometimes what may happen in a problem, this previous problem, I could have, if I wanted to, once I figured out the sine and the cosine, I could have figured out the tangent by just using this fact. I could have plugged in 3/5 for the sine and 4/5 for the cosine, and hopefully you remember how to work with complex numbers. In this case, the 5's cancel out and you're left with 3/4. So you say the tangent theta is 3/4, and of course that's the same answer I would get as if I used the trig definition. Sorry you didn't see that, but so I said the tangent of theta equals the sine over the cosine. Just for fun, I plugged in my sine and my cosine. I'm going to simplify it at 3/4, which is the same. All right, so that's the start of defining the trig functions based upon the right triangle. In the next lecture, we'll continue to look at trig functions in right triangles.